Hello friends and welcome at my channel. Today I'm doing a new topic about the Euler's function, and I've done a few videos about that, so I decided to make a separate playlist for this as well. So there's going to be a playlist for Euler's number, Euler's function, its derivative of ln, and maybe a few other things. But now I would like to show you that there is a very special property if we're talking about e to the power of x, which I want to show you. So if we're considering an exponential function, let's say f of x equals to 2 to the power of x, it's normally going like this. We are going through the point 0, 1, since every allowed base to the power of 0 is giving you 1. If you look at 5 to the power of x, let's say g of x is 5 to the power of x, well, it goes down faster, but it also rises faster, as you can see. And there is also an interesting function, let's call it k of x, which is x plus 1, and if we plug it in, we'll see a very nice and interesting situation. So x plus 1 goes like this, through the point x plus 1, it crosses the red function 5 to the power of x, but it also crosses the black function 2 to the power of x. And what we would like to understand, and first of all what we see here, is that we are crossing twice. All right, so the first intersection point considering 5 of x is happening before the origin, before 0, 1, before we get to the 0, not the origin, sorry, 0, 1, and then the second point is 0, 1. With the black one, it's exactly the opposite. We are crossing firstly at 0, 1, and later on we are crossing 2 to the power of x. Well, I can draw some more pictures, but I maybe use software. So this is exactly what I've been talking about, and now let us maybe add a few more functions. So if we have, let's say, z that we are defining as, well, let me make it a bit bigger for you. All right, so z of x, which is maybe, let's say, 1.5 to the power of x, and we add it here, then you see what's happening. So I have to kind of go further with x values, so make 5 out of 2, and then you see later I'm still crossing the blue one. This is 1.5 to the power of x, but this is still 2 points, one at 0, 1, and the second one is happening later. So that means 2 to the power of x is crossing twice at 0, 1 and later, and 1.5 to the power of x is kind of having the same behavior as 2 to the power of x, but the second point is happening later. All right, so if we have L, which we are defining as 4, or let's say maybe firstly 7 to the power of x, let's see what's happening here. So we add L as well to this list, especially if you look, I just defined G. So what we want to understand, we keep K in the list. We don't care about F anymore. Let us see what is happening if we're having G, K, and L. So G is 5 to the power of x, as you can see, and L is 7 to the power of x. So you see what's happening. This is 5 to the power of x, the red one. The yellow one is 7 to the power of x. And maybe you see, I have to change once again my window settings. So we go down. Now you see, maybe, yeah, it's clear now. The yellow function is crossing at 0, 1 and before the red point, before the red curve. Okay, so that means if we're moving from 2 to the power of x lower to 1.5 to the power of x, the second crossing point is kind of moving away. And if we're moving from 5 to the power of x to 7 to the power of x, the second point, we still have 2 points. 0, 1 is always given, but the second point is also moving away. So the distance between those two crossing points is getting bigger. All right, And now, well, let's see what is happening if we're not moving from 2 to the power of x lower and 5 to the power of x higher. Let's see what's happening if we are dealing, let's say, with r that we are defining as, well, let's call it 2.2 to the power of x. I'm not exactly putting like 2.5 or something, because it's very close to something what I want to show you, and we cannot see maybe clearly what's happening. So r is 2.2 to the power of x and f. So we would like to see the difference between r. So we have f, r, and we do not need g anymore. So let's see what's happening here. Now you see we have to change the settings again, maybe going a bit higher. Well, now you see that this curve, just maybe too far away, 2 or 3, yeah, slightly better, but I'm too far away, right? 2 here as well. Yeah, now it's clear. Yeah, so we're still crossing twice everywhere. We have 0, 1, and the second 2 points are crossing points are coming later, and you see maybe that the yellow one is a bit sooner than the green one. So, and the yellow one is a slightly bigger function, which is 2.2 to the power of x. So that means if we're moving down from 2, we're getting further away. If we're going up from 2, like slightly bit to up to 2.2, we're going up. All right? And what will happen, now let's do it again, let's define q, which is 4 to the power of x. What will happen here? Well, if we're having, well, k is still our x plus 1, let's say g and q. G and q we want to have. Well, you see now this is g and this is q to the power of x, and you see q is moving slightly closer to 0, 1. If you cannot see it clearly, I'll change maybe once again the settings and you'll be able to see it. Now you see, so these are the 2 intersection points at 0, 1 both, and the second point is here and there, and the green function is 5 to the power of x. It falls faster, but it goes also faster. And the second is 4 to the power of x. So that means the distance between 2 points is getting smaller. All right, this is our observation so far. The question is there a base, some unknown a to the power of x? Is there a function p of x, which is a to the power of x, which is not crossing the x plus 1 twice, but only touching it once at 0, 1. So is there a base a with a property that x plus 1 would be a tangent at 0, 1, which means a to the power of x is behaving like 1 plus x if x is approaching 0. With other words, is it possible to find this a? So let us try to figure it out. And since we're talking about limits, it doesn't matter from which side we're coming in this situation. So it doesn't matter whether x is coming from the left-hand side approaching 0 or from the right-hand side. It should be approaching 0 somehow. So let's say x is running towards 0 from the right-hand side. So that means if x is very small and positive, a is roughly 1 plus x to the power of 1 divided by x if x is running towards 0 from the positive side. That means a can be written as a limit x towards 0 from the positive side of 1 plus x to the power of 1 divided by x. All right? And, well, let's substitute. Let's call n equal to 1 divided by x. So x is 1 divided by n. And now we've chosen x to be very small positive. So that means n is very big positive. So it goes to infinity, which means we're having a limit n towards infinity. Move my picture away. N towards infinity, and then we're having 1 plus 1 divided by n to the power of n. But wait a second, isn't that an Euler's number? There you go. This is E. I link my introduction to compound interest video here. It's going to be part 1 in the new produced playlist. And this is the Euler's number that we discovered previously, okay? And so e to the power of x is the only function, and e is the only base, which is just touching 1 plus x, not crossing it. And let me show it again here. So now we're really defining a new function. Let's call it maybe w, which is exp of x, so the e function. And let's see what's happening here if I add it. So let's just only take k and w here, and let's take it from -2 maybe to 3, and y from -2 to 5. Let's see what's happening here. Something is wrong. That's nice. Have I defined the function? No. X of x should be fine. Okay, let's see. Maybe now. Yeah, that's better. So you see, I'm only touching. Really, I'm only touching. So that means that e to the power of x is behaving approximately as 1 plus x if x is very close to 0. And that means the limit of x running towards 0 of e to the power of x minus 1 divided over x is equal to 1, since they are behaving equally if x is running towards 0. This is a very important limit which we're going to be using and many times, and this is one of the biggest properties of the Euler's function. Okay, thank you guys for watching. See you in the next video. All the best. Bye bye.